This is the 6th video devoted to Bessey Shuffle diagrams. And let's just take a quick review of a few definitions. A shuffle S is said to be a Bessey Shuffle if and only if S preserves or inverts Bessey sequences. Recall the Bessey sequences of order 8 are 1 0 0 1 0 1 1 0 and its inversion 0 1 1 0 1 0 0 1. Also recall that the position values of the cards we will look at have been color-coded as follows. Positions 1, 4, 6, 7 have been color-coded black, and positions 2, 3, 5, 8 have been color-coded red. And in what follows, one of two outcomes will occur. Either the cards that originally began in positions 1, 4, 6, 7 will remain in those positions, as well as cards in positions 2, 3, 5, 8 will remain within those positions. If such an outcome occurs, we describe it as indicated here. And that's in contrast to something we call an inversion of the sequence. So what happens here is cards that were originally in positions 1, 4, 6, 7 get moved to somewhere among the position values 2, 3, 5, 8. And vice versa. Cards that began in these positions get moved somewhere to these positions here in the set A. And if that occurs, we say inversion has occurred, and it's denoted as indicated here. Finally, before we move into demonstrating the new shuffles for today, recall the Bessey sequences 1 0 0 1 0 1 1 0 and its inversion 0 1 1 0 1 0 0 1 can be described in the following two ways. In the case of the Bessey sequence up above, we see that the ones are in positions 1, 4, 6, 7, and the zeros are in positions 2, 3, 5, 8. For the inversion of this Bessey sequence, namely this one down below, the role of the zeros and ones switch places. The ones are now in positions 2, 3, 5, 8, and the zeros are in positions 1, 4, 6, 7. Our first Bessey shuffle for today is called a pairwise transpose. Now that's a name I've given this shuffle. I'm not aware of any name for this shuffle. So as always, we begin with our ordered packet 1 through 8, and we perform the shuffle. Then we look at the resulting new ordering of the packet. From there, we will write the outcome in terms of Cauchy's two-line notation for a permutation, and then convert that to cycle notation, which is one-line notation. So let's go ahead and show you the pairwise transpose. Okay, so how this works, maybe let me take a moment and explain the reason for the name and how there are different ways to accomplish this precise shuffle. Okay, so a transpose is where if you have two things, if you change their positions or orders, that's called a transposition. A pairwise transpose is where you take the top two cards and then you switch them like this. And then you take the next two cards and switch them like this. And then you take the next two and switch their order. And then you take the next two and switch their order. That is actually a pairwise transpose. Now, as we'll see, there are perhaps easier ways of accomplishing that same permutation. And I'll show you in just a moment how to do that. But now that we've done the pairwise transpose, let's go ahead and take a look at the new ordering of the cards so that we can write out the permutation for this shuffle. So as you can see, the new ordering is 2, 1, 4, 3, 6, 5, 8, 7. So in Cauchy's two-line notation, we get the following. The top row is always 1 through 8, and then we get 2, 1, 4, 3, 6, 5, 8, 7. Converting that to cycle notation, we find the following. That 1 goes to 2, so I have an arrow from 1 to 2. 2 cycles back around to 1. So we get a completion of that cycle. It's called a 2-cycle, which is also referred to as a transposition, which is interesting if you think about the name of the shuffle. So we have a transposition there. Now what happens with 3? 3 goes to 4. So I have an arrow from 3 to 4. And then 4 goes to 3. So it wraps around, completing a second 2-cycle, or a second transposition. What about 5? 5 goes to 6, and then 6 returns back to 5. So we get a third transposition. And finally, 7 is sent to 8, and 8 goes to 7, so it wraps back around. So we get our fourth 2-cycle, or our fourth transposition. Color-coded, the cycle notation for our permutation is as follows. Remember, positions 1, 4, 6, 7 are color-coded black, and positions 2, 3, 5, 8 are color-coded red. So we see that black 1 goes to red 2, which wraps around to black 1. Red 3 goes to black 4, which gets sent back to red 3. Red 5 goes to black 6, which goes back to red 5. Black 7 goes to red 8, which gets sent back to black 7. So we can see that something very important has happened here. Each value gets sent to a value of the opposite color. And as we know from our previous videos, this means an inversion has occurred, which simply means that the cards in positions 1, 4, 6, 7 get moved somewhere to positions 2, 3, 5, 8, and vice versa. So we have this situation resulting. Since inversion occurs, we can illustrate that by using our Bessey sequence 1001, 0110 to show that the pairwise transpose, when performed on this packet of 8 cards, will invert this sequence. So let's go ahead and perform the pairwise transpose in the way that I would normally perform it. The first time I showed you, I did it in hand, which can be a little awkward. So the pairwise transpose that I actually showed you just a moment ago can be accomplished as follows. You deal out one card into one pile, and then a second card into that first pile. So you do 1, 2, 1, 2, 1, 2. And now we're going to stack 1 on top of 2. Those 4 cards get stacked on top of 3, and those 6 cards get stacked on top of pile 4. And that's equivalent to what we just did a moment ago, where we did it in hand. Now what will occur, the Bessey sequence we began with, which was 1, 0, 0, 1, 0, 1, 1, 0, will now be inverted to 0, 1, 1, 0, 1, 0, 0, 1. So indeed, this shuffle inverts Bessey sequences. And because of that, we say that the pairwise transpose, with stacking as indicated here, is a Bessey shuffle, and that's because it preserves, or in this case, inverts Bessey sequences. Let's go ahead and take a look at the graph. It's on the top row, far left, and this is a graph we have not seen before, nor will we see it in subsequent shuffle diagrams. So here is the cycle notation of our permutation. We've indicated that inversion has occurred. And so what we get is we just get double arrows between pairs of values. So between 1 and 2, there's a double arrow. Between 3 and 4, there's a double arrow. Between 5 and 6, a double arrow, and between 7 and 8, a doubled arrow. So cards will just switch back and forth within each of these pairs each time this shuffle is performed. Consequently, this shuffle has order 2. If you perform it twice, it resets the packet to its original order. Now, at the end of this video, I will show you an application that involves all 4 of the shuffles that we are talking about today. But before we do that, let's go on to our second shuffle. Our second shuffle is also referred to as a pairwise transpose. And that's because the only difference here will be the stacking order, as you will see. So for this shuffle, we begin with an ordered packet 1 through 8, and we're going to now perform this shuffle. Now recall, a pairwise transpose is where you deal the first top 2 cards onto each other. So 1, 2, 1, 2, 1, 2, and then 1, 2. Okay, that is a pairwise transpose dealing of the cards. Now this time we're going to stack 4 on top of 3, and those 4 cards on top of 2, those 6 cards on top of 1. So what we're doing is we're simply stacking from right to left. And something I don't think I made clear with the previous shuffle that we just did, so let me just point it out. In the first shuffle we did in this video, this stacking is simply a description of stacking the piles from left to right. That's all we did earlier. Now we're stacking the piles from right to left, where the numbering of the piles is assumed to be pile 1, 2, 3, 4. So number 4 is over here. So the notation indicates that we stack from right to left. That's the only difference. Now, of course, it will lead to a new ordering of the cards. Okay, so this is the new ordering that we get, and it's kind of a curious one if you look at it. It's simply a packet reversal. So in Cauchy's 2-line notation, our permutation is described as follows. So we have 8, 7, 6, 5, 4, 3, 2, 1 as our new ordering. Writing that in cycle notation, we get the following. 1 goes to 8 and 8 goes to 1. So we get a transposition or a 2 cycle. 2 goes to 7 and 7 goes to 2. So it wraps around. We get a second transposition. 3 goes to 6 and 6 goes to 3. Here is our third transposition. And 4 goes to 5 and 5 goes to 4. So here's our fourth transposition. So whether it's apparent immediately or not, this right here is the cycle notation for a packet reversal of 8 cards. Color coding the numerals 1 through 8, we obtain the following. Recall that positions 1, 4, 6, 7 are color-coded black, and position values 2, 3, 5, 8 are color-coded red. The reason for the color coding is to aid us in detecting whether there's been a wholesale replacement of cards in these positions and they've been moved to these positions. So has there been an inversion is what we call it. So has this occurred? So in the color coding, we can see that black goes to red 8 and red 8 goes to black. Red 2 goes to black 7, which cycles around to red 2. Red 3 goes to black 6, and black 6 goes to red 3. And black 4 goes to red 5, which gets sent back to black 4. So we can see here that each value gets sent to a value of the opposite color. So this is an indication that inversion has occurred. Why don't we quickly demonstrate that using our quintessential Bessey sequence 1001 0110. So what we have shown here is that we should get the inversion of this sequence. So let's perform the shuffle. So once again, you deal 1, 2, 1, 2, 1, 2, and then 1, 2, and now here we're stacking from right to left. So what we should get is the inversion. So we should get 0, 1, 1, 0, 1, 0, 0, 1, and we do. So looking at this sequence here that resulted from the pairwise transpose in which we stacked from right to left, let me just point out the zeros and ones switched places in some fashion. But in particular, what has happened is the first position card, which used to be a 1, got switched with the 8th position card, which used to be a 0. Because right here we see that 1 goes to 8 and 8 goes to 1. Similarly, the second card, which is now a 1, switched places with the 7th card, which is now a 0. So that 0 here used to be here, and that 1 there used to be there. So that's why we have a 2, 7, 2 cycle. And similarly for positions 3 and 6 and positions 4 and 5. Looking at the shuffle diagram for this pairwise transpose in which we're stacking from right to left, we get a diagram that is identical to one that's coming up later in this series, namely Shuffle 47. And as indicated, this shuffle that we've just performed is equivalent to just reversing the order of all of the cards. Doing so leads to this Bessey Shuffle diagram. There's a double arrow between 1 and 8. There's a double arrow between 2 and 7. Also a double arrow between 3 and 6. And finally a double arrow between 4 and 5. For our third shuffle today, it's also a transposition, but I call it a judicious transposition. That's why I have the letter J. J is standing in for the word judicious, which means wisely chosen or wisely determined. Now the first two shuffles today, we did a stacking from left to right, and then we did a stacking from right to left. Here we're going to do a more complicated stacking. It's also referred to as a leapfrog stacking, as you will see. So I begin with the order packet 1 through 8 and perform the shuffle. So it begins the same. I go 1, 2, 1, 2, 1, 2, 1, 2. And now the stacking is as follows. Pile 1 gets stacked on top of pile 3. And I've referred to this as a leapfrog stacking. It's leaping over its neighbor. Now pile 2 gets stacked on top of pile 4. So you can think of that as a leapfrog action. So it's leaping over that one. And to finish, we're going to stack the left pile on top of the right. So left on right. Okay, so what is the new order that results from this shuffle? Well, let's take a look. It looks like it's 2, 1, 6, 5, 4, 3, 8, 7. So in Cauchy's two-line notation, we get the following. We get 2, 1, 6, 5, 4, 3, 8, 7 as the bottom row of our two-line notation. Converting that to cycle notation, we obtain the following. 1 goes to 2, so I have an arrow from 1 to 2. 2 goes to 1, so 2 cycles back around to 1. So we get a 2 cycle, or in other words, a transposition. 3 goes to 6, and 6 returns to 3. So we get a second transposition. 4 goes to 5, so I have an arrow from 4 to 5. And then 5 goes to 4, so it cycles back around, completing that 2 cycle, which is also called a transposition. Finally, 7 goes to 8, so I have an arrow from 7 to 8, and then 8 goes to 7, so it wraps around. So that completes our fourth 2 cycle, or in other words, our fourth transposition. Color coding the digits, we obtain the following. Recall that the color coding of the digits is as follows. Positions 1, 4, 6, 7 have been color coded black. Positions 2, 3, 5, 8 have been color coded red. This will help us keep track of whether cards in these positions stay within those positions, or is there a wholesale replacement with the cards in these positions here, 2, 3, 5, 8? If there is, we say that an inversion has occurred, and we represent it like this. If no inversion occurs, then of course it's represented like this. So we see that black 1 goes to red 2, which cycles around to black 1. Red 3 goes to black 6, which cycles around to red 3. Black 4 goes to red 5, which cycles around to black 4. Black to red 8, which cycles around to black 7. So we see here that each value gets sent to a value of the opposite color. And when that happens, inversion has occurred. So why don't we go ahead and illustrate that inversion does indeed occur. Here is our quintessential Bessey sequence. So if we perform this shuffle on this labeling of the cards, we obtain the following. So here you do a 1, 2, 1, 2, 1, 2, 1, 2. That's always the same for a transposition. Now the stacking is different. We're going to stack 1 on top of 3, 2 on top of 4, and then the left pile on top of the right. So what we should get is the inversion of the Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0, and the inversion is 0, 1, 1, 0, 1, 0, 0, 1. So an inversion has indeed occurred. Taking a look at the graph for this shuffle, we see the following. That there's a double arrow between 1 and 2, a double arrow between 3 and 6, a double arrow between 4 down here, which is kind of hiding, sorry about that, to 5, and then a double arrow from 7 to 8. And as we'll see, there is no other shuffle that we have or will present in this series that has that identical shuffle diagram. So in that way, it is unique among the shuffles we will present in this series. Our last shuffle for today is also a judicious transpose, but this time the stacking will be pile 1 on top of pile 3, pile 2 on top of pile 4. Now that's the same as the previous shuffle, but this time we'll stack the right pile on top of the left. And it gives, as we can see here, a very different shuffle. Because if you remember, the previous shuffle was a product of transpositions, 2 cycles. And I should point that out, that the previous shuffle, shuffle 23, has order 2. So if you perform that shuffle twice, you reset the packet to its original order. This one has order 4. So you would have to perform this shuffle 4 times to reset the packet to its original order. Okay, so let's go ahead and prove that this is the cycle notation for this permutation. So we'll begin with our ordered packet and we'll perform our shuffle. So the transpose, it always begins with dealing 1, 2, that, 1, 2, 1, 2, 1, 2. Now, the stacking is going to be pile 1 on top of pile 3. We can think of that as kind of a leapfrog stacking. Pile 2 on top of pile 4, also a leapfrog action. But this time, in contrast to shuffle 23, the previous shuffle, we're going to stack the right pile on top of the left. So what is the new ordering that results from that? Well, let's take a look. We get 4, 3, 8, 7, 2, 1, 6, 5. So in Cauchy's 2-line notation, we obtain the following. The top row, of course, consists of just 1 through 8, and the bottom row is this new ordering here, 4, 3, 8, 7, 2, 1, 6, 5. We can convert this to cycle notation as follows. 1 goes to 4, so I have an arrow from 1 to 4. 4 goes to 7, so I have an arrow from 4 to 7. 7 goes to 6, so 7 goes to 6. And then 6 returns back to 1. So that completes this cycle. And in particular, it's a 4 cycle. What about the other 4 values? What happens to them? Well, 2 goes to 3, so I have an arrow from 2 to 3. 3 goes to 8, so there we go. 8 goes to 5, so an arrow from 8 to 5. And then 5 cycles back around to 2. So that completes a second 4th cycle. And that accounts for all of the position values of these cards. If we color code the cycle notation of our permutation, we obtain the following. Recall that the digits are color coded black if they are 1, 4, 6, 7, and the position values 2, 3, 5, 8 are color coded red. So we see here that inversion does not occur. Black 1 goes to black 4, which goes to black 7, which goes to black 6, which wraps around to black 1. So, quote, the black values stay within their respective set. Red 2 goes to red 3, which goes to red 8, which goes to red 5, which wraps around to red 2. So the cards in position values 2, 3, 5, 8 stay within those 4 position values. And so we see that the following has occurred. Each value gets sent to a value of the same color. And when that happens, inversion does not occur. Instead, we say that there's been a preservation of these sets of position values. Okay, so to see that clearly, the 4 cards that began in positions 1, 4, 6, 7 stay somewhere in that set of position values 1, 4, 6, 7. Similarly, for a complement, the cards that originally began in positions 2, 3, 5, 8 will stay somewhere within that set of position values 2, 3, 5, 8. So we're looking at this outcome right here. So applying this shuffle to our Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0, we should expect to get back this same sequence form. So let's go ahead and just perform that shuffle one more time. So we go 1, 2, 1, 2, 1, 2, and then 1, 2. Now we're stacking the first pile on top of the third, the second pile on top of the fourth, kind of a leapfrog stacking, and then the right pile here gets stacked on top of the left pile. So we should expect to get back 1, 0, 0, 1, 0, 1, 1, 0. Now it's very important to realize that even though we got the same sequence form back, it doesn't mean that the cards have not moved around. In fact, we know that all of them have moved around. There is not a single card here that has been returned to its original location before we performed the shuffle that we just did. Why is that? Because as we can see in our cycle notation of this permutation, we don't have any fixed points. Every single value gets moved to a different position than the one in which it started. And so why don't we go ahead, I'm going to go ahead and just set this down. And then I'm going to also put down the sequence that we just got earlier that led to the cycle notation up above for our permutation. Okay, I just want to make clear what has happened here. So going all the way back to the introductory video in this series devoted to Bessey Shuffle diagrams, remember, how do we interpret this? So we have a 1 going to a 4. What does that mean? That means first place is now going to what was in the 4th position. Is that true here? Has the first position been replaced by what was in the 4th position? It most certainly has, because we began with the order packet 1 through 8. Okay, moving on. 4 being sent to 7. What does that mean? That means 4th place has now been assigned to what was originally in 7th position. And that is the case. What about 7 here? The 7th place, after our shuffle, has been assigned to what was originally in the 6th position. And finally, sixth place goes to 1, which means sixth place goes to what was originally in position 1. And we see that that's the case here. And then we have a similar interpretation for the second 4 cycle. So let's apply it to the 0s and 1s. So let's go back to 4. We know that first place in this sequence, remember, when the cards are facing down, this card is the top one, the first one. Okay? So the new first place is being assigned to the card that was originally in the 4th position. Well, what does that tell us here? We've performed the shuffle, this very shuffle. So what that means then is what was in the 4th position now gets moved to first place. Okay? So if you undo the shuffle, if you go back before that shuffle was performed, the precise card that was right here is now at the top of the packet. Similarly, 4th place now is being assigned to what was originally in the 7th position right here. So what started out here has been moved to this position right here. In other words, 4th place. And maybe to do one more, 7th position. After that shuffle's done, 7th position now has gone to the card that was originally in the 6th position. So if you go back in time, what was in this position has been moved to 7th place. Okay? And then I guess just to finish, 6th place here, after the shuffle is completed, goes to the card that was originally in the 1st position. So before the shuffle took place, that first 1 at the top of the packet of 8 cards has now been moved to 6th place. So I know that's a lot to take in, but it's really the only way to understand clearly the movement of these cards. And so I encourage you, if you watch the first video, the introductory video in this series, it goes through and gives an analogy using a special packet of cards to explain the true meaning and a helpful interpretation of permutations and how to read permutation notation. Okay, and finally, let's take a look at the shuffle diagram for this final shuffle in our video today. So here we have a product of 2 4 cycles. There they are. Over here we've indicated that inversion has not occurred, and we know that from down here. Remember, black value positions get assigned to other black value positions, and red value positions get assigned to other red value positions. Now the shuffle diagram looks like this. So 1 goes to 4, so you have to focus on here. 1 goes to 4, 4 goes to 7, 7 goes to 6, and then 6 goes back to 1. Okay, so 1 goes down here to 4, 4 goes up to 7, 7 goes down to 6, 6 goes way over here to 1, and that completes that 4 cycle. We also say that the values 1, 4, 6, 7 are members of the same orbit. In a similar fashion, if we begin at 2, we see here that 2 goes to 3, 3 goes to 8, 8 goes to 5, and then 5 wraps around to 2. So 2 goes to 3, 3 goes up here to 8, 8 goes straight down to 5, and then 5 comes up here to 2, completing that second 4 cycle. And that also constitutes an orbit. Note that down at the bottom here, we indicate that this particular shuffle is the inverse of shuffle 26, which will be coming up in our next video. So this shuffle will undo the effect of shuffle 26, as we will see. Finally, let's show an application of all of this. Okay, so here's an application involving the 4 shuffles that we demonstrated today. I need to emphasize, as always, that not only can these 4 shuffles be performed within this demonstration and not undermine anything that we hope to accomplish, any of the shuffles in this entire series can be performed in any order and in any quantity. That is the amazing thing. And it's because the only shuffles I'm showing you are Bessey Shuffles, and Bessey Shuffles preserve or invert Bessey sequences. And as will become clear by the time that we finish the series, many, if not a majority, of the systematic shuffles used today are indeed Bessey Shuffles. They either preserve or invert Bessey sequences. So you can see my selection of cards here. So let me just gather those up. So let's go ahead and perform these shuffles in any order and in any quantity, actually. Now, of course, you're not here, so I'm going to have to make choices for you. But if you were here, you would freely be given the option to choose one or more of these shuffles in whatever order that you would like. So why don't we begin with shuffle 23, let's say. Okay, so that's a judicious transpose. Okay, now all of these shuffles begin with the same dealing out, right? Hopefully I've made that clear. The only difference is the stacking. And that stacking makes an enormous difference to the outcome of the ordering of the cards. So for shuffle 23, the stacking is as follows. We take the first pile and stack it on top of the third. You can think of that as leapfrogging over its neighbor. We take the second pile and stack it on top of the fourth. You can also think of that as a leapfrog action. And then finally, we stack the left pile on top of the right, like that. Okay, so we've performed shuffle 23. Which one would you like next? 22? Okay, that would be just fine. So we deal out into these little pairs. 1, 2, 1, 2. Okay, so what's the stacking now for shuffle 22? It's stacking from right to left. Okay, so if you look at the notation there, it's just a way of describing stacking these piles from right to left. Which one would you like next? Shuffle 21. Okay, we can do that one next. So we do 1, 2, 1, 2, 1, 2. And now for shuffle 21, the stacking is from left to right. Okay, so we go from left to right. And at any stage, you can check the ordering of these cards, and it will be different because of the shuffle being applied. The cards are truly being scrambled here. Let's see, the last one that we haven't done, if we're going to just perform each of these once, which we wouldn't have to. We can perform any of these as many times as the spectator calls for. But let's go ahead and finish with shuffle 24. I believe that's the one we haven't done yet. So shuffle 24. Okay, the 1, 2, 1, 2. These aren't sticking. 1, 2. And now the stacking for shuffle 24 is the leapfrog. So we leap over its neighbor, 1 on top of 3. Leap over its neighbor, 2 on top of 4. But this time we're stacking the right pile on top of the left. Okay. Now please know that we can perform any of these additional times and in whatever order you would like. Okay. But let's go ahead and just kind of finish. So what I'm doing here is I'm just dealing out the cards into 2 piles, 4 cards each. And then what I'm going to do is a fun little shuffle. It's called the Klondike. This is where you take the bottom and top card off as 1. Sorry about that. These are new cards and strange cards because they stick. And then I'll take the top and bottom card off as 1, like that. Okay, that's the Klondike. And what does that result in? Okay, well, let's take a look here. Oh, that's interesting. Oh, 2 red, 2 black, 2 black, and 2 red. You've got to be kidding me. How did I match up exactly the card colors of these 8 cards? Now this could have had a written I could have had a written prediction off to the side that I would open before we show these cards to say that we have successfully somehow, with all of the choices made by you, the spectator, we have successfully paired up cards of the same color. And that would be true. We would finish in this way. Okay, so how does this work? So sorry about these cards, like I said, are not technically bicycle cards, playing cards. They're Zelda cards, actually. So they have a different feel to them. Okay, so let me explain the way I started, and you could start differently if you wanted. Okay, so what I did was I built a Bessey sequence relative to card color. Okay, well, think about what would that be, a Bessey sequence relative to card color. Well, we would need something like red, black, black, red, followed by black, red, red, black. Okay, so this would be one version of a Bessey sequence relative to card color. The other one that we could have done is black, red, red, black, red, black, black, red. That would be the inversion of this one, relative to card color. So this is where I began. If you want to begin here, that would be great. Just kind of set up the cards this way. To the untrained observer, if they look at this little packet of cards, they will see no special organization whatsoever. They could even stare at it for a while. They'll probably see nothing of interest. Okay, they really won't. But if you want to use that clever technique that Warner Miller, who's one of my subscribers, sent in, and I've used it a few times in some of my videos regarding Bessey sequences, what you can do is begin with, let's say, the 4 red cards on top, the 4 black cards on bottom, and maybe even openly show these if you would like. You can just show them that, okay, we have 4 red cards and 4 black cards. And then perhaps off to the side on a piece of paper, maybe you've written a little prediction saying all of the pairs will consist of cards of the same color. So within each pair, you'll have either 2 red or 2 black. Okay, so you could have a written prediction if you want. Okay, so what you do is just gather these up. So the top half is red, top 4 are red, bottom 4 are black. Okay, so Warner Miller came up with this wonderful triangle deal that converts this structure type to a Bessey sequence. So this is where you deal into a triangle clockwise. So you deal clockwise till you run out of cards, and then you pick up the first packet first, the one that you dealt out first, and then stack in counterclockwise order. Now what this is guaranteed to do is it will convert it, let me just do it this way, it will convert it to a Bessey sequence of some sort. Here it's converting it to one in which the leading color is black, which is just fine. So this is a Bessey sequence relative to card color. Black, red, red, black, red, black, black, red. Okay, so that's a kind of a classy way of converting that original structure into a Bessey sequence. Once it's a Bessey sequence, it's going to be protected against the effects of all of the shuffles that I will be showing you in this series. And in particular, it will be protected from the 4 shuffles we've introduced today. Now, what do we mean by protected? We mean that this packet will either be returned to its original color organization as a Bessey sequence, or its inversion, where the red cards switch places with the black cards in some fashion. Okay? So in that way, this packet truly is impervious or unharmed by all of the shuffles that we will show you in this series. Mathematically, we would say it's invariant. And to be super precise, it's invariant up to inversion. What does that mean? That means we either get the original packet structure back as a Bessey sequence, or we get an inversion of that. And either one will serve our purposes just fine. We actually don't care which one we get. We don't care if this packet is inverted or not. And as we've talked about today, some of these shuffles invert, like the first one here, that inverts the sequence or the packet. This one does as well, number 22. 23 does as well, but 24 does not invert it. And so at this point you can perform as many of these pairwise transpose as you like. So maybe we'll just do a couple just to show you. Maybe we'll do 24, which doesn't invert it, and then we'll do one that does. Okay, so 24. So this is where you do it into just 1, 2, 1, 2, and 4 piles. Okay, and then 24, what are we doing? We're leapfrogging. We're doing one, stacking pile 1 on top of pile 3, 2 on top of pile 4, and then here for shuffle 24, we're stacking the right pile on top of the left. Okay, and if you were here, I'd just have you randomly choose one among shuffles 21, 22, 23, since they invert it. So maybe you'll say 23. Let's do 23, I guess. So you go 1, 2, as always, 1, 2, 1, 2, 1, 2. And then here it's also the leapfrog. So 1 goes over 2 onto 3. 2 goes over this neighbor here onto 4. Now this time we're stacking left on right. If you look at shuffle 23, we're stacking left on right. Okay? So rest assured that we could perform any number of any of these today, or any of the ones that I have or will be showing you. Now what I did to finish was, so the way that we're going to finish, there's many different conclusions. There's many different ways to finish, as you're probably seen if you've watched other videos in this series. But the way that I decided to use, that I haven't used thus far in this series, is to create pairs of cards where within each pair the cards are of the same color. Okay, so the way that I did it was I dealt into 2 piles, a left, right, which seems like a perfectly fair way to kind of scramble the cards. And then you pick up either pile. Now let me just show you the organization of the cards so that you can understand why the Klondike Shuffle is going to work for us. So let me just show you. So we've done the left, right. Well, what's the organization of the cards, before we do anything else? In fact, let me show you both of them, because you'll see that really what it is, it's just 2 halves of a Bessey sequence. That's all it is. It's just 2 halves of a Bessey sequence. Red, black, red, and then black, red, black. So if you stack those in any order right here, it's still a Bessey sequence. Why is that? Because that was one of the first shuffles we showed you in this series, the LR shuffle. Stacking left on right or right on left, it preserves or possibly inverts Bessey sequences. So anyway, we're looking under the hood. So this is the color composition of the cards. Same thing here. Okay. So in particular, notice that we have a red on top. Remember, if we turn the cards face down, this is the top card. That's the bottom. So we have a red on top and a red on bottom. So the Klondike is where you pull off the top and bottom cards off as one. Well, those will get pulled off together. They're both red. The next 2 cards are both black, so they'll get pulled off together. They're the remaining pair. Same thing here. If I pull off the top card and the bottom card, they're both black, and then the remaining 2 cards are red. So you're guaranteed to separate these cards into 4 piles, in which within each pair, the cards will be of the same color. Okay, so what I did, which I fumbled with because of these cards being a bit sticky. So a Klondike is where you pull the top and bottom card off as one. You're taking the top and bottom off as one. Hopefully there's just 1 there. That leaves me with 2. Same thing here. Top and bottom off as 1. Set those down and then set down the remaining pair. These are guaranteed to be of the same color within each pair. Okay, so you can go like that, go like this, go like that, and then go like this, and bring out your written prediction, if you had one, stating that you would perfectly separate the cards into pairs of the same color, And if you want to do something a little bit more advanced and give it a little bit of thought, you'll realize that it's not hard to do. Not only could we state with confidence that each pair would consist of cards of the same color, because of the organization of the cards, if we were to peek, so this is before we do this is right after doing any one of our Bessey Shuffles over here. So we're Bessey Shuffling it. So we have the pack of 8 cards. Now we're going to do a left, right, and so forth, okay? So before we do the left, right, that packet of 8 cards, if you were to glance and note the color of the bottom card of that packet, you would have enough information so that you could deduce in the end exactly which pair would be red and exactly which pair would be black. You would know exactly which pairs. And so what you could do is, with the cards face down, like they would be face down, of course, like this. And you could, kind of hover your hand over and go, this one feels like that one feels like it's red. A red pair. Oh, yeah, I got it right. What about black? Or any of these just like, wait, these are, within each pair, they're all the same. That's weird. Well, what color are these? Oh, yeah, those are clearly black. I can just feel it. Yeah, I got them. What about this one? Let's see. That one's red. I'm just seeing red in my mind's eye. I'm seeing red. Is that true? It is indeed. And then, of course, really by elimination, these would have to be black. How in the world was I able to feel that, to deduce that after all of the random shuffling that we did, dictated by you, the spectator? You told me how to mix those cards thoroughly. And then I just kind of separated them into piles of 2 in kind of a crazy way. And somehow I could tell that all of them were of the same color within the pair. But beyond that, I knew which ones were red and which ones were black. How in the world was I able to do that? Okay, so anyway, that's another application involving Bessey Sequences and Bessey Shuffles. So I encourage you to take a look at other videos in this series, and if you've looked at the previous ones, go ahead and move on to video number 7. So thank you for watching.